Hello everybody. So I'm making a series of videos for you for this new internal that you have. It's modern physics and it's worth 3 credits, and it will be a written test, a 50-minute written test next term. So just an introductory lesson today really, and this is a follow-up of what you did in year 12, which was atomic and nuclear physics. Now this modern physics is actually in 3 little parts. So there's one part which is called nuclear physics, and that's what I'm going to be doing first. And then there's another part which is about spectral lines. That's atomic physics. And then there's a third part that is called photoelectric effect. All this is about 10 or 12 lessons long, and so you have plenty of time to go over this. Right, so just kicking off, all the things that we know about motion, forces, electricity, they've been there a long time, and they form what's called classical physics. Now modern physics, this came about much later, and that is dealing with very, very small particles like the atom. Now years and years ago, about 1896, there was a French person called Henri Becquerel, and he was actually studying minerals. And what he did was he took a piece of uranium ore and he wrapped it in light-proof paper, and he put it into a drawer which also had photographic paper in that drawer, and that photographic paper was also wrapped with light-proof paper. Later on, when he looked at the photographic paper, he found that it was affected without actually being exposed to light, which told him that this uranium was giving out some sort of energy. And this is what we know today as radioactivity. 2 years later, about 1898, the Curies, Pierre and Madame Curie, they actually isolated polonium and radium. Now these are much, much more highly radioactive compared to uranium, and their health was actually affected at the end of it. So all this leads us to, brings us to thinking more about the structure of the atom. And as you know, the atom is made of a central nucleus which has protons and neutrons. The protons are positively charged, the neutrons have no charge. And outside the nucleus, you have the electrons. Now the electrons are held there because of this electrostatic force of attraction between a positive charge, which is the proton, and the negative charge, which are the electrons. Okay, now I'm just going to introduce a few new terms to you. Now protons and neutrons, because they are in the nucleus, are collectively known as nucleons. So a nucleon could be referred to as a proton or an electron. And the total number of protons and neutrons in the nucleus is called the nucleon number. That's the total number of particles in the nucleus, and this is the number of protons plus the number of neutrons in the nucleus. Okay? The atomic number is what defines the element, and that is the number of protons. Okay, it's a number of protons. Now a proton itself has a special symbol. A proton is really just the nucleus of a hydrogen atom. So the symbol for a proton is 1H1. This is how you represent elements. So you write the symbol for the element, and then you put the mass number there and the atomic number here. Mass number is same as nucleon number. Now, if you think a little deeper about what's happening inside the nucleus, because nuclear physics is the realm of physicists, and they look at what's happening inside the nucleus. What happens to the electrons is actually the realm of the chemists, because that's what's involved in chemical reactions. So any sort of change that takes place to the nucleus involves a nuclear reaction. Okay? Now, if you put positive charges together, a whole lot of them, they wouldn't like to be close to each other. They would all fly apart because of the force of repulsion. So I wonder if you've ever thought, what is it that holds the nucleus together? There must be something that's responsible for all these particles held so tightly within the nucleus. So that brings me to telling you about the 4 fundamental forces in nature. There's actually 4 fundamental forces, 2 of them that you're aware of already. So one is the gravitational force, and anything that has mass has a force of gravity. It is always an attractive force and it acts over long distances. Now this is what holds the Earth in orbit around the Sun. This is why the Moon goes around the Earth. So be familiar with that. Then there is the electrostatic force, which is the force between charged particles. So that could be attractive or repulsive depending on the nature of the charge. Now there are 2 more forces. So the next force is actually the strongest of all forces in nature, and it is called the strong nuclear force. So this strong nuclear force. Now this is the force that actually holds the nucleus together, and this force is an attractive force, and there's an optimum distance when this force is strongest, and it doesn't depend on charge. So it's a force of attraction between a neutron and a neutron, or a proton and a proton, or a neutron and a proton. Okay, so that's what holds the nucleus together. And then the 4th force is called the weak force, which is actually responsible for beta decay. So these are the 4 forces in nature. All right? Let me just write the board. Let's move on to the next one. Okay, the next thing that we're going to look at is the stability of the nucleus. Now, for elements from 1 to 20, that's all the way up to calcium, the stable nuclei are the ones whose proton-neutron ratio is about 1:1. So the moment there is a difference in the proton-neutron ratio, that's when the nuclei tends to be unstable. And what unstable nuclei do is, in an effort to become stable, they give out energy in the form of radiations. And this radiation could be emitted as an alpha particle, or a beta particle, or a gamma ray. Okay, so we've learned about radioactivity last year. So this is a nucleus trying to become more stable. Now that actually brings us to isotopes, which are actually different forms of the same element. So isotopes are those elements, because it's the same element, they all have the same number of protons, or the atomic number is the same. I've written 3 carbon, the symbol for carbon 3 times, and they all have 6 protons in the nucleus because they have the same atomic number. The one that we're familiar with is carbon 12 because it has 6 protons and 6 neutrons. This is really stable. And then there's carbon 13, which has got 6 protons but 7 neutrons. And then there's carbon 14, which has got 6 protons but 8 neutrons. And this one's quite unstable, it's radioactive. Okay, now I'll just talk to you a little bit about radioactivity so we're not missing out on that. So like I said, you have what's called alpha emission, alpha decay. You have beta decay, and you could also have gamma radiation, which are given out. Now the thing is, as there are more and more particles in the nucleus, as the number of nucleons increase, the number of protons increase as well. So if you come to think of it, there's really 2 forces that is acting inside or within the nucleus of any atom. So one of them is what we call the electrostatic force of repulsion, because of the positive charges trying to break it apart. Now, and then there's also the strong nuclear force. So for nuclei with too many protons or too many neutrons, if the balance is not right, that's when they tend to become unstable, and then they undergo radioactive decay. So when an alpha particle is lost, given out, a nucleus loses 4 particles from in the nucleons, and the atomic number comes down by 2, simply because an alpha particle is really a helium nucleus. So this is how you represent an alpha particle. So it's a symbol for alpha, or you can write it as a helium nucleus. Okay? And then you have beta decay. Now, beta particles are fast-moving electrons, but these are not electrons from the outside of the nucleus. These electrons are emitted because a neutron changes into a proton, and it gives out an electron, and the electron is what comes out as a beta particle. So, beta particle electrons have hardly any mass compared to alpha, compared to your protons or neutrons, and this is how an electron is written, or a beta particle. Now, sometimes the unstable atoms or nuclei have too much of energy within themselves, and in spite of giving out an alpha particle or a beta particle, so they often lose that excess energy by giving out gamma radiation. Now, gamma rays are just high frequency electromagnetic waves. They have no charge and no mass, and that is how you write the symbol for a gamma ray. Okay, so that'll do for an introductory lesson, and I hope that made sense, and bye for now.